right, so section 4.5, you learned about the dimension of a vector space. And as you know, the dimension is defined as the number of vectors in a basis for a vector space. And of course, you had exercises where you had to find the column space and the null space for a matrix. And then you had to find and then once you read, well, I need to be a little more careful. Yeah, well, you needed to find a basis for the column space of a matrix, a basis for the null space of a matrix. And once you found those bases, then you could state the dimension of the null space and column space based on the basis of each of those. And in section 4.6, we take that idea a little bit further by talking about something called the rank theorem. So what I'd like to do is share, hold on here. I want to share the textbook. So let me bring that up here. And I have a few examples I want to do with you. But first, I'd like to give you a little bit of a guided tour of this section 4.6. Rank. Okay, so now let me blow this up a little bit here. This off here. So this section, section 4.6, takes a look inside a matrix and reveals useful relationships hidden in rows and columns. For instance, imagine placing 2,000 random numbers in a 40 by 50 matrix A, okay, and then determining the maximum number of linear independent columns in A and the maximum number of linearly independent columns in the A transpose. Remarkably, the two numbers are the same, okay? And as you'll soon see, the common value is called the rank of the matrix, the rank of the matrix. So first of all, the textbook talks about something new, something called the row space, the row space. So you understand what a column space is, okay? Hold on here, one moment. I always go back to definitions just to, but the column space is, of course, hold on. It's the span of the column vectors of the matrix A. Okay. Well, the row space would be the span of the row vectors of a matrix A. So what they have here is they have this matrix A. Okay, it is a 4 by 5 matrix, and they have the row vectors. Now, we normally think of vectors as column vectors, but with the row space, we think of the rows as vectors. And there are 4 row vectors here, 4 row vectors, and the row space would have to be, the row space of the matrix A would have to be a subspace of R5 spanned by those row vectors. Okay, and it's natural to write row vectors horizontally. However, they also may be written as column vectors if it's more convenient. Okay. All right. So that's what a row space is. That's what a row space is from section 4.6. Okay. Now, what I want to do, I want to go down to example 2 here. And I really should use the mouse to go up and down. But here in example 2, they want you to find bases for the row space, column space, and null space of the matrix. Okay, that's what they want you to do. So you learned, of course, how to find bases for the column space and the null space of a matrix. So to find, I mean, of course, what you're going to do is you're going to row reduce. You're going to row reduce the matrix A. And in this case, they're row reducing the matrix so that it's in echelon form. Okay, it's in echelon form. And that's what you see here. So how many pivot columns do you see? Well, actually, let's go to the column space first, because that's what we're used to. What are, like, there are five columns here, 5 vertical columns. Which columns correspond to the pivot columns? Okay, which columns correspond to the pivot columns? First and second, is there any other pivot columns? That's right, Mikkel, the fourth one as well. So the pivot columns that when you row reduce the matrix A to echelon form, which is what matrix B is, you identify 3 pivot columns, columns 1, 2, and 4. That means then that the basis for the column space of A would be the column vectors in the matrix A that correspond to the pivot columns. So the first column, second column, and fourth column of the matrix A forms a basis for the column space of A. Okay, let me just see here. I heard a chat. Let me see, is there and Binyam, that's correct. So the column space of A is 3-dimensional. So the column space of A is a subspace of R what? The column space of A is a subspace of R what? R, is the column space of A a subspace of R5? Would be a subspace of R. Would it be a subspace of R3? How many out in each the vectors live where? If you look at this basis for the column space of A, the vectors are all 4x1 vectors, so they live in R4. They live in R4. Therefore, the column space of A, okay, which is the span of those 3 column vectors, is a subspace of R4. However, the column space of A is a 3-dimensional subspace of R4. Right? The column space of A is a 3-dimensional subspace of R4 because 3 vectors are needed for the basis of the column space of A. And I appreciate all answers. It's okay to have, to offer an answer and it's wrong. It's okay. You're learning, right? Now, the basis for the row space of A would be as you see here. Okay, it would be as you see here. This would be your basis for the row space of A. Maybe I'll just highlight this. So what you're doing there is you're basically looking at pivot rows. Okay, and there are 3 pivot rows. Okay, but if you flip the rows and turn them into columns, it's a little easier to see it. But I mean, that's all there is for the basis for a row space. Okay, and let me just see here if there's anything sort of okay, so I don't think there's anything magical about that. Let me see here. Well, I will say though that the dimension we'll notice that the that for the row space of A, the basis has 3 vectors. Just like the column space of A, the basis has 3 vectors. And that's no accident. The dimension for the row space is 3. The dimension for the column space of the matrix A is 3. And the dimensions of the column space and the row space are going to be equal. Now, I'm not proving that, but it is a fact. It's a fact by something called the rank theorem, which you're going to see in a moment. Also, to find a basis for the null space of A, well, you know how to find the null space of A. You have to solve the augmented matrix. And what they do is they, solve the augmented matrix. I mean, want to be careful. You're solving the system AX equals 0. But if you row reduce A, they row reduce the matrix A into the matrix C and solve the system CX equals 0, which is equivalent to solving AX equals 0. And you find out that you have 2 free variables, and then therefore the basis for the null space of A. If you write your solution of your null space out in parametric vector form, you'll see that the solution will be x3 times this first vector here, plus x5 times that second matrix. How many recall doing that in their homework that was due today? How many recall doing that? Sure, and this is a reason too, Kevin remembers it, Benjamin, this is a reason too why I don't like homework assignments to be due, like just the day before the exam, right? Because I like to have my assignments, the due dates paced out. What you learned is helpful for this what you learned in section 4.5 is helpful for this discussion. Where the null space of A, which is the span of those, what's the dimension for the null space of A? What's the dimension for the null space of A? It's going to be 2. It's going to be 2. And let me just see here, one moment. All right, so the dimension for the column space of A was 3. The dimension for the null space of A is 2. 3 plus 2 adds up to what? 3 plus 2 adds up to 5. Oh, how many columns were there in matrix A? How many columns were there? 5. Oh, that's interesting. 2 plus 3 equals 5. Okay, and that's no accident. That's no accident. Okay, there is a theorem called the rank theorem. Okay, and incidentally, the rank is defined as the dimension of the column space of A. That's how the rank's defined. But the rank theorem states that the dimensions of the column space and the row space are the same of a matrix. The dimensions of the row space and column space of a matrix A are the same. Okay, and it turns out that the rank of A, which is the dimension of the column space of A, plus the dimension of the null space of A, that equals n, where n is the number of columns in the matrix A. That's known as the rank theorem. Okay, and it's a theorem that we're going to do a couple of examples, and it's a theorem that is actually very neat, very, very cool. But are there any questions before we move to the examples? I'm going to have you copy a few down, but are there any questions? I'll mention something here. The row space of A is the same, by the way, as the column space of A transpose. Okay, the row space of A, of course, would be the same as the column space of A transpose. That's that's I think obvious. All right, well, if there are no questions, let me go ahead and go to the examples here. All right, let me give you a moment to copy this example down. Okay, so in this problem, we're wondering if a 6x9 matrix could have a two-dimensional null space. All right, could a matrix that has 6 rows and 9 columns, would it be possible for that matrix to have a two-dimensional null space? Right, and of course, what we're going to need to use is, to help us, is the rank theorem. So you have to be careful on these kind of questions. In MyMathLab, a lot of times there's multiple choice, or parts of them are, you just have to be careful. You don't want to answer too quickly, right? Because it's not a quick question. It takes a little bit of thought. But the rank theorem says that the rank of A, which is the dimension of the column space of A, plus the dimension of the null space of A, that is going to equal n. And that's when you have an m by n matrix. So this is your rank theorem. We can use this rank theorem from section 4.6, theorem 14. We can use it to help us answer this question. So let's think about some. I mean, what do you intuitively want to do with this rank theorem? Intuitively, what do you want to do? We have a two-dimensional null space. Okay, so all right, that's right. Plug in the numbers. Cal and Noah are correct. Plug in the numbers. All right, we're going to do that. So the dimension of the null space is, I'm going to to be 2. Okay. And n is 9. So what's the rank of A have to be? It's got to be 7. Good, everybody. So what we're asking here, really, what we're equivalently asking is, could the rank of A, could the dimension of the column space of A possibly equal 7? All right, so I'm getting some, Sega doesn't think so. Noah doesn't think so. Okay, and well, and Noah makes a point that how many rows are there for this 6x9 matrix? How many rows are there? There's 6. So what's the, and I got to be a little bit careful here. I got to be a little bit careful. We can kind of see there's an issue. Let me just bring up the solution. Noah, you're on the right track. Let me bring up the solution here so I can be very organized. So the answer is no. Now, actually, let me give you a moment to copy this down, okay? And then we'll talk about it. All right. Let me give you a moment to copy the solution down. Okay. So and again, I wanted you to just think about it a little bit. So we have a 6x9 matrix, we'll call it B, and it has a two-dimensional null space. Then by the rank theorem, the dimension of the column space of B, which is the rank of B, has to be 7, because 7 plus 2 equals 9. But the column vectors in B are in R6 space. They're in R6 space, right? Because there are 6, every column vector in B has 6 entries, 6x1 vectors. So they all live in R6 space. Therefore, the dimension of the column space of B, which is the number of vectors in a basis for B, cannot exceed 6. Right? It's like if you, an analogy would be like if you have three-dimensional space. How many vectors are needed in three-dimensional space to form a basis? 3. That's right, James. 3. You know, I, J, and K, or in our case, you know, E1, E2, E3. All right. So if 3 vectors are needed in three-dimensional space, you need 3 vectors to form a basis. Oh, well, what if you added a 4th vector? Would you have a basis anymore? No, you wouldn't. You'd have too many vectors. So similarly here, since these vectors, these column vectors in B live in R6 space, the rank of the base, the rank of this matrix B, which is the dimension of the column space of B, you know, it's the, you know, the span of the column vectors of B. Okay, I want to say this the right way. The dimension of that couldn't be more than 6. It cannot exceed 6. I want to say this the right way. The vectors, the column vectors of the matrix B, all live in R6 space. Okay, they all live in R6 space. So the dimension of the column space of B cannot exceed 6. All right, does that make, are there any questions? No, Sega, if it were 6x8, oh, wait, hold on. Okay, so if Sega's saying, what if we had a 6x8 matrix instead of a 6x9 matrix? In that case, you could have a two-dimensional null space, because the column space, the dimension of the column space could be, I want to say it's the right way. The column vectors of B, I always go back to the basics. The column vectors of the matrix B live in R6. So a basis for the column space of the matrix B you could have 6 vectors in the basis. That's possible. Okay, that's possible. You know, so that is possible, Sega. In that case, you could have a two-dimensional null space if the matrix A were a 6x8 matrix. Okay, are there any questions on this? Any questions? All right, Kevin's good. Very good. All right. All right, let's look at another example. Okay, let me move to another example. Okay, let me give you a moment to copy this one down, this example. Okay, so in this example, we're wondering if it's possible for a non-homogeneous system of 7 equations. Incidentally, a non-homogeneous system would mean that A times X equals what? Good, Binyam, equals B. If A times X were equal to the 0 vector, that would be a homogeneous system. But if A times X equals B, and B is not equal to the 0 vector, then we have a non-homogeneous system. So we're wondering if we had a non-homogeneous system of 7 equations and 6 unknowns, is it possible for that non-homogeneous system of 7 equations and 6 unknowns to have a unique solution for some right-hand side of constants? What theorem are we going to need to use to definitely to help us here? What special theorem from section 4.6? The rank theorem. That's right, Solomon. Okay, Well, let's go ahead and look at the solution. All right, let's look at the solution. Okay, the answer is going to be yes. So let's consider, let's consider what we have here. Here's our system of equations. There are 7 equations and 6 unknowns, which means that the matrix A has to be a 7 by 6 matrix. The vector X has to be a 6 by 1, of course. That would make sense, 6 unknowns. And then the matrix B over here is 7 by 1. All right, I just kind of like to spell things out a little bit. And let's talk about the matrix A. So since the matrix A has at most 6 pivot positions, okay, at most, okay, why would that be? Why would that be? A is a 7 by 6 matrix. Seven rows, 6 columns. But they're saying that A has at most 6 pivot positions. Where are they getting the 6 from? Where's that coming from? Ah, good, Binyam. You have 6 columns. You have 6 columns. Okay, so it doesn't, the columns, now where do the columns live? What space do the columns of A live? They live in R7. The column vectors of A are 7 by 1 vectors, 7 rows, right? So the column vectors of A live in R7. But the matrix A, since the matrix A has 6 column vectors, at most you would have 6 pivot positions. You know, just think of something easy, like, 1, 0, 0, 0, 0, 0. I'm thinking of my matrix, constructing my matrix A in my mind, and I'm thinking of a very kind of easy matrix A. Columns of the matrix A are 7 by 1, so the first column could be this, second column could be this, and we got 4 more columns. So for my little example, again, the matrix A doesn't have to be this easy, but any matrix A can be reduced into reduced echelon form, so you can identify pivot columns. What would the last one have to be? Could you tell me what the last one would have to be, the last vector here? And again, this is just my example. You could think of a different example. Okay, hold on. Couldn't the 1 be there? Yeah. Okay, so, you'd have, the last row would be all zeros. That's right, Binyam. In my example. Well, actually, no. Actually, that's true for any matrix A. If you do the row operations, I put a 6 there for like 6 columns. Yeah, any matrix A, the last row, when you get it in reduced echelon form, you're going to have a row of zeros at the bottom. Okay. Okay, does that make sense? Okay, so you're all right. Good, good. I was actually in the exam, I was pleased with how people did on the multiple choice. Very few people did perfect on them, but you did a good job overall. Overall, good job on that exam. I could tell you worked hard. All right, well, let's continue here. Very good. So the rank of A would be then less than or equal to 6. And so by the rank theorem, the dimension of the null space of A would have to be, which is 6 minus the rank space of A, that would have to be greater than or equal to 0. If the rank of A is less than or equal to 6, the dimension of the null space of A would have to be greater than or equal to 0. But again, think what we're asking here. We're trying to see, is it possible for this non-homogeneous system of 7 equations and 6 unknowns to have a unique solution for some right-hand side of constants? Is it possible? It is possible. It is possible. Suppose the dimensions of the null space were equal to 0. Okay, suppose the dimension of the null space were equal to 0. Then that means that AX equals B would have no free variables. Would have no free variables. Because let me see here. In that case, the rank of A would equal 6, and there's no free variables. And so the solution to AX equals B, if it exists, would have to be unique. Would have to be unique. So I'm thinking that if this system of equations, this 7 equations and 6 unknowns, 2 of the equations would have to be the same, I believe, for this to happen. I have to be a little careful. I don't want to just say things, but let me just check one thing. Let me just check on that. One moment. One moment. Hold on. One moment. I got to be a little careful on that. I got to be a little bit careful on that. I have to think about that a little bit more. But are you comfortable with this statement that AX equals B, that system would have no free variables? And you know why? Actually, here's why. Here's why. Whenever you find the null space, okay, what if you write the null space in parametric vector form, what variables are in front of the the basis vectors of the null space? What kind of variables are in front of those basis vectors in the null space? What are those variables called? They're free variables. That's right, Noah. So if dimension of null space equals 0, then you don't have any free variables. And so the solution AX equals B, if it exists, would have to be unique. Okay. because there's no free variables. If there's, let me just see here. If there's no free variables for this for the homogeneous system AX equals 0, then AX equals B would also have no, the non-homogeneous system also would have no free variables. Okay, does that make sense? Are there any questions on that? All right, let me stop the recording.